Hi everyone, in this particular tutorial video we'll be discussing week 8's tutorial questions. The tutorial questions have already been uploaded on your Moodle shell, so please do make sure you attempt them before watching this tutorial video, right? Let's start. The first question is question number 24 of your textbook, right? So the first question states that we need to determine graphically the Q point for the circuit, right? For this particular circuit. We have to determine the Q point using the transfer characteristics curve, right? This is a transfer characteristics curve that has been given. So just by visually inspecting this JFET circuit, we can just see that the JFET has actually been self-biased. So what that means is that your gate voltage is equal to 0, right? So in this particular case, what we have to do is to calculate the gate source voltage at ID is equal to 0, and we have to calculate the gate source voltage at ID is equal to IDSS, right? So you'll be getting 2 points, and by connecting those 2 points, we are generating a DC load line. So if you plot the DC load line on the same axis as your transfer characteristics curve, the point where the transfer characteristics curve intersect the DC load line is the point where you get your Q point, right? So if we start, so let's say if we set ID is equal to 0, so when your ID is equal to 0, your VG is equal to VG minus, right? VG minus VS, right? So which is equal to VGS, right? So your VG is equal to 0, so your VGS is equal to negative VS, right? So your VS is given by ID RS, right? Your VS is equal to ID RS, so that simplifies the formula to your VGS is equal to negative ID RS, right? So since your ID is equal to 0, your RS value is already given in the circuit, so substituting the values you get, VGS is equal to 0 volt, right? That's the first point. Your gate source voltage is 0 volt at ID is equal to 0. So that's the first point. This to calculate the second point, we have to set your ID is equal to IDSS, which is equal to 5 milliamps. So again, the formula remains same. Your gate source voltage is equal to negative ID RS, right? So currently your drain current is equal to 5 milliamps, right, which you have set. So and your RS value again that has been given in the circuit. Substituting the values, you get negative 1.65 volt as your gate source voltage at ID is equal to 5 milliamps, right? So plotting these two points on the same axis as the transfer characteristics curve and joining them, you get the DC load line. So the point where it intersects the transfer characteristics curve is your Q point, right? So graphically determining the Q point, you get VGS is approximately equal to negative 0.95 volt and ID is approximately equal to 2.9 milliamps at the Q point, right? Moving on to the second question, which is question number 27 of your textbook. Again, we have to determine the Q point for the JFET with voltage divider bias. So this is the voltage divider biased JFET circuit, for which we have to determine the Q point using the characteristics curve given. For such kind of biasing, what we have to do is to actually set ID is equal to 0 and calculate your VGS, which will be your first point of your DC load line, and the second point of your DC load line is given by setting VGS is equal to 0 and calculating your ID, right? So using those 2 points, you can actually draw the DC load line, right? So when you draw your DC load line on the same axis as your transfer characteristics curve, you'll get the Q point, which is the point where the two graphs intersect, right? So just examining the JFET circuit with voltage divider bias, you can just see that the gate voltage is given by the voltage divider, right? So to determine the first point, we have to set your ID is equal to 0, right? So initially you know that your gate source voltage is equal to gate voltage minus source voltage. So when your ID is equal to 0, the current across the RS is equal to 0 as well. Your current across RS is equal to 0. So what that means is your source voltage becomes 0, right? So in such cases, what happens is your gate voltage is equal to your gate source voltage, right? You can see over here. So to calculate your gate source voltage, you just need to calculate your gate voltage. So your gate voltage is given by the voltage divider, right, which is R2 upon R1 plus R2 multiplied by VDD. So you can directly substitute the values from the diagram, right? So directly substituting the values, you'll get 2.2 mega ohms holding upon 5.5 mega ohms multiplied by 12 volt, which is equal to 4.8 volts. So that means that 4.8 volts of gate source voltage at ID is equal to 0 ampere. So that will be your first point. To determine your second point, you have to set your VGS is equal to 0, right? So when you set your VGS is equal to 0, your VG is equal to your VS, right? So your VG is equal to VS, right? So you can set your VG is equal to VS. So to determine your ID, what you can do is you can divide your source voltage divided by your RS, right? So VS upon RS is equal to ID. So your source voltage is equal to gate voltage, which is equal to 4.8 volts divided by RS, which is 3.3 kilo ohms, right? So you'll be getting 1.45 milliamps, right? So that is your second point. So that means 0 gate source voltage at 1.45 milliamps of drain current, right? So using those 2 points, right? Using these 2 points, you can actually draw the DC load line. So when you draw your DC load line, right, on the same axis as your transfer characteristics curve, so the point where the two graphs intersect is your Q point. So your Q point is equal to ID is approximately equal to 1.9 milliamps and VGS is equal to negative 1.5 volts, right? Moving on to the third question, which is question number 41A of your textbook, right? We have to determine the VDS for this particular circuit, given that IDSS is equal to 8 milliamps, right? So we know that IDSS is given, right? So our IDSS is equal to our ID, right? So VDS is equal to VDD minus IDRT, right? So you can directly substitute the values. Your VDD is equal to 12 volt, right? Minus your ID is equal to 8 milliamps, right? Which is equal to IDSS, and your RT is equal to 1 kilo ohms, right? You can directly substitute the values, and you'll get VDS, which is equal to 4 volts. Moving on to the last question, which is question number 42 of your textbook, right? So for this particular question, we have to determine the gate source voltage and drain source voltage for the enhanced MOSFET, right? So this is the circuit for which we have to determine the VGS and VDS. So to determine the VGS, you can see that you already know that gate source voltage is given by gate voltage minus the source voltage, right? So you can see that there is no source resistance, so that means our source voltage is equal to 0, right? So our source voltage is equal to 0. So what that means is our gate voltage is equal to our gate source voltage, right? So our gate voltage is at the moment given by the voltage divider, so which is also equal to our gate source voltage, right? So using the voltage divider, we can calculate our gate source voltage, which is R2 upon R1 plus R2 into VDD, right? So you can get the values from the diagram itself. So directly substituting the values, you get 4.7 mega ohms holding upon 14.7 mega ohms, which is 14.7 mega ohms is R1 plus R2, right? 10 mega ohms plus 4.7 mega ohms, right, multiplied by 10 volts. So you get gate source voltage as 3.2 volt, right? So now we have to determine our drain source voltage, right? So we know that our ID on is equal to 3 milliamps at gate source voltage of 4 volts, right? And our threshold voltage is 2 volt. So what we can do, we can actually determine the characteristics constant, right? So using that particular characteristics constant, we'll be able to determine the ID at a particular given gate source voltage, right? So using the characteristic equations for the E MOSFET, which is ID is equal to K into VGS minus VGS threshold length squared, we can make K the subject of the formula, right? So if we make K the subject of the formula and substitute the values for ID on and the threshold for voltage, right? So our ID on is 3 milliamps, halting upon VGS is 4 volts minus 2 volt halting squared. So we can get our K, which is equal to 0.75 milliamps per voltage squared, right? So that is our K. So the K value remains constant throughout for any given VGS value for a particular E MOSFET. So using that particular K, we can actually determine our ID. So we know our threshold voltage, right? So we know our gate voltage. So we can determine our ID. So our ID is equal to K into VGS minus VGS threshold halting squared. So using the K value that we have calculated over here, that is 0.75 milliamps per voltage squared, and substituting the VGS at which we want our ID, right? So VGS at which we want our ID is 3.2 volts, right? So we substitute 3.2 volts, right? And our threshold voltage, our threshold gate source voltage is already given, that is 2 volt. So we can also substitute that and calculate our ID. So our ID for gate source voltage of 3.2 volt is equal to 1.08 milliamps, right? So that's our ID. So our drain source voltage, right? To calculate our drain source voltage, we can substitute. We can actually subtract the drop across the drain resistance from the VDD, right? So our drain source voltage is equal to VDD minus IDRT, right? So we have already calculated our ID over here, right? So we can use this ID. So VDD is already given in the diagram, directly substituting the values. 10 volt minus 1.08 milliamps into 1 kilo ohms. 1 kilo ohms is our RT, right? So if we directly substitute the values, we can calculate our VDS, which is equal to 8.92 volts, right? So we have calculated our VGS and VDS, right? So that's all we had to calculate. So I left out some of the questions at the beginning, right? So let's complete those as well, right? Question number 10. The following parameters are obtained from a certain JFET datasheet, right? VGS off is equal to negative 8 volt and IDS is equal to 5 milliamps, right? Determine the values of ID for each value of VGS ranging from 0 volt to negative 8 volt in 1 volt step, and plot the transfer characteristics curve from these data, right? So you know that ID is equal to IDS S into 1 minus VGS upon VGS of halting squared, right? So your IDS value is given, your VGS value is given. So what you need to do is change your VGS at a step of 1 volt from 0 to negative 8 volt and calculate your ID value at each of that particular VGS value, right? So we'll be starting off at 0 volt, right? Then we'll be moving on to negative 1 volt, negative 2 volt, negative 3 volt, and so forth, right? And calculating the ID value using this formula, right? So your ID value at VGS is equal to 0 volt is 5 milliamps. Your ID value at VGS is equal to negative 1 volt is 3.83 milliamps, and your ID value at VGS is equal to negative 2 volt is equal to 2.81 milliamps. The ID value at VGS is equal to negative 3 volt is 1.95 milliamps. ID value at -4 volt VGS is equal to 1.25 milliamps. ID value at VGS is equal to -5 volt is equal to 0.703 milliamps. ID value at VGS is equal to -6 volt is equal to 0.313 milliamps. ID value at VGS is equal to -7 volt is equal to 0.078 milliamps, while ID value at VGS is equal to -8 volt is equal to 0 milliamps, right? So using the points, right? So that means VGS is equal to 0 volt, and at that particular point ID is equal to 5 milliamps. So you plot your points, right? VGS is 0 volt, 5 milliamps. VGS is equal to -1 volt. ID value is 3.83 milliamps, right? So -1 volt, 3.83 milliamps, right? So likewise you plot for all VGS and ID values, right, for which you have calculated, and you'll be getting a graph of something like this, right? So that's for question number 10. The next question is question number 21. Using the curve, using the curve in figure 867, determine the value of RS required for a 9.5 milliamp drain current, right? So using this particular curve, right, we have to calculate our RS value at drain current, or ID is equal to 9.5 milliamps, right? So at ID is equal to 9.5 milliamps, right? You'll be getting your VGS value approximately equal to -2 volt, right, from this particular graph, right? So you know your VGS, right? From this graph you'll be obtaining your VGS that will be equal to -2 volt, right? And your ID value is 9.5 milliamps, right? So to calculate your RS, you just divide VGS by ID, right, and take the absolute value of that, right? So it will be -2 volt divided by 9.5 milliamps, right? You'll be getting 211 ohms as your RS, right? So that will be your answer for question number 21. Moving on to the next question, question number 22, right? Set up a midpoint bias for a JFET with IDSS equal to 14 milliamps and VGS of is equal to -10 volt. Use a 24 volt DC source as supply voltage. Show the circuit and resistor values. Indicate the values of ID, VGS and VDS, right? So at midpoint your ID is equal to IDSS divided by 2, right? So you'll get a ID of 7 milliampere, right? So that will be your ID at midpoint, right? To get your VGS at midpoint, you need to divide your VGS off by 3.414, right? So that is equal to -10 volt divided by 3.414. You'll be getting your midpoint VGS value as -2.93 volt, right? To calculate your VGS, to calculate your RS, what you need to do is your RS value. To calculate your RS value, what you need to do is divide the VGS by ID, right? Yeah. So your RS value is given by VGS divided by ID, right? Which is equal to 2.93 volt, right? Divide by 7 milliampere. So your resistor value will be 419 ohms, right? So your source resistance will be 419 ohms, but the nearest standard value is 430 ohms, right? So you will be using the standard value to draw the self-biased circuit, right? And to calculate your RT value, what we need to do is
the RD value over here is given by VDD minus VD divided by ID, right? So in this particular case, your VD is equal to VDD divided by 2, right, at midpoint. So your VDD is given 24 volt minus your VD, which is equal to VDD divided by 2, that is 24 divided by 2, which is equal to 12 volt, right? Holding upon 7 milliampere, right? So you'll be getting your RT value equal to 1.7 kilo ohms, right? So the nearest standard value is 1.8 kilo ohms, right? And the RG, this particular RG is basically to ground to ensure the input is I mean the gate voltage is grounded, right, to ensure that. So we just select a RG value of 1 mega ohms, right? So putting all this into a diagram form, you'll be getting a self bias midpoint JFET setup as something like this, right? Moving on to the next question, question number 23, right? I think this is the last question that I had missed. Question number 23, we need to determine the total input resistance in figure 868, where IGSS is equal to 20 nano ampere at VGS is equal to negative 10 volt, right? So your total input resistance is given by your RG parallel with your input resistance, right? So which is equal to your Rin value is given by VGS, right? VGS divided by IGSS, which is equal to negative 10 volt divided by 20 nanoamps, which is equal to 500 mega ohms, right? That's your Rin. Your Rin total is RG parallel with Rin, which is equal to 10 mega ohms parallel with, right, your RG value is given, right, 10 mega ohms, and your Rin, which you have just calculated, right, 500 mega ohms. So you parallel both of these, right? So you will be getting the Rin total, which is equal to 9.8 mega ohms, right? So that's it for this week's tutorial. Thank you.